So yesterday we talked about finding missing parts of a triangle. Do you guys have any questions on that out of the homework or anything? Is it going okay? Remember, there are two things. We can be looking for a missing angle, or we can be looking for a missing side. If we're looking for an angle, now we're always given the right angle when we're dealing with right triangles, of course. So we'll be given the right angle. But if we're looking for a missing angle, we'll be given two sides. Morning. So let's say in this triangle here, we are given that this side over here is 11 centimeters, and this side down here is 18 centimeters. And we're looking for this angle right here. We'll call that angle A. The first thing we have to do is identify the two sides. Now, of course, this is the easy one to identify. That's the hypotenuse, but we're not given that one, so that one doesn't matter. We're given the two legs. And remember, the legs depend on which angle we're looking at. So when we're looking at this angle, this leg is the adjacent. And this leg is the opposite. So we have the adjacent and the opposite sides of the triangle. There are two functions, if you look through your list of functions, that use adjacent and opposite. One is cotangent, but that's not on our calculator. The other is tangent. So our definition of tangent is the tangent of an angle is the opposite side over the adjacent side. Now we're looking for the angle, so we don't know the angle. But the angle we're looking for is angle A, so I'm going to put A in there for the angle. The opposite side is 11, the adjacent side is 18. Now, since we are looking for an angle, the way we solve this equation is to use an inverse function. That's the second function. Remember the tan -1, sine -1, cosine -1. So we're going to do an inverse tangent, or tangent -1. Cancels out the tangent, leaves us with A here, equals the inverse tangent of 11 over 18. So second tangent, 11 divided by 18, close the parentheses, is 31.43 degrees. Now, of course, once we have that angle, if I go up here and label this 31.43, we know that these two have to add up to 90 degrees because this one's already 90. And the triangle, of course, always adds up to 180. So we can subtract from 90 to get this one as 58.57 degrees. So we can find one angle. Once we have one angle, the third angle, the other angle falls into place. Of course, finding the hypotenuse here, we don't even really need trig. That's just the square root of 18 squared plus 11 squared, or Pythagorean theorem, right? A squared plus b squared equals c squared. If we are looking for a side, now again, we're always given the right angle. Pretend that looks like a right angle. And we always have to be given at least one side. So let's say I'm given it that's 30 centimeters. And I'm given this angle here is 68 degrees. Let's say I want to find this side right here. I'll call this side B. I'll call this angle A, B, and C. So this is side little a, little b, and little c. So when I'm looking for a side, Unlike up here where I had to be given two sides, here I have to be given one side and one angle. Because if I have two sides, of course, I find the third side just with a squared plus b squared equals c squared. I don't have to use trig for that. But again, I identify the side I have. So the side given here is the 30 centimeters. That, of course, is the hypotenuse. And then identify the side needed. The side that we're looking for. We said that was this side that we were looking for over here, side B. That is, according to the angle we're given, if we're given angle A, side B would be the adjacent side because it's next to that angle. So we have hypotenuse and adjacent. Could be a secant, but that's not on our calculator. What else could it be? Cosine of an angle is adjacent over hypotenuse. So now we're going to fill in. In this case, we know the angle. The angle is 68 degrees. The adjacent side is B. That's what we're looking for. The hypotenuse is 30 centimeters. When we are looking for a side, the way we go about solving this is we make it into a proportion. We put that over 1. And now we can cross, multiply, and divide. So here we have cosine of 68 times 30 divided by 1, which of course, no, you don't have to actually divide by 1, but 11.24 centimeters. Now, if we're in centimeters, going to a couple decimal places is adequate. If we're in inches, you should probably go to at least 3, at least go to the thousandth. So that's our generic triangles. You guys seen a sign bar in the shop at all? Have it in the hallway? They don't use it anywhere? Okay. A sign bar is a very, very precisely machined piece of material. By the way, a good sign bar should have it labeled on the side of it what temperature it is to be used at. Most of them they'll say like between 68 and 72 degrees. Because the precision is thrown off if you're outside that temperature range because it can expand. I mean, you're talking about thousandths or even 10,000ths of an inch, but it can expand enough to, if you want to be very precise, it can expand to get out of tolerance. But a sign bar, piece of material that is rounded on both ends, yeah, pretend those look round. You're catching on. Oh yeah, I am very aware of my lack of artistic talent. What's that? Yeah, true. To point out how bad my artwork is. Hey, I've gotten pretty good at drawing stick figures now. I'm proud of that. So anyway, it's very precisely machined, and it's rounded on the ends so you can set it on bevels. So you can set it up on angles, and it'll still be precise. But the distance from, this is setting on a surface here, the distance from where this makes contact, or the tangent point there to the tangent point here, is usually either exactly 5 inches or 10 inches, depending on the sign bar. The most common ones are 5 inches. I don't know what do they have down here. That's a 5-inch, I'm assuming. Is it a 10-inch in the case? Okay. And it's set. It's built like that so that if you set it, like I said, on a bevel like this, what would you use, by the way, to very precisely build up a height here to set this end on? Gauge box. Very good. So you can have this end sitting on gauge box, and that's why it's as big as it is, rounded off, so it can set up on top of that. And the distance from this point of tangency to this point of tangency will still be exactly that 5 or 10 inches. because it moves around the point of the circle exactly the same. So what this does is it creates a hypotenuse of a triangle. And with these gauge blocks here, the triangle is going to be like right here, and this will be a right angle. It creates a precise hypotenuse of a triangle. Let's say that this is a 10-inch sine bar. So it creates a hypotenuse that's exactly 10 inches. One of the applications of a sine bar is to create a very precise angle here. So now I'm going to go back to just drawing my triangle. This is the 10-inch sine bar here. And let's say I want this angle to be exactly 18.43 degrees. I need to know this height here. I need to know what to build up my gauge blocks to be. How do I find that height? Yes, I have this angle here. This is the hypotenuse. This is the opposite side. It is the sine that uses the opposite of the hypotenuse. Of course, the cosecant would also use hypotenuse and opposite, but that's not on our calculator. So we're trying to stick to sine, cosine, and tangent for use of the calculator. What's that? They just decided it wasn't worth it. Well, it all goes back to the days when they actually used tables instead of calculators. And in the tables, in order to list it off, you had to list off every degree and every fraction of a degree to make it precise. So to list off all those fractions of degrees, you didn't want to have a column for every trig function. So things like secant and cosecant, they just calculated as the reciprocals of sine and cosine, rather than making a column on the table for them. So that when they programmed the calculator, they didn't bother putting them on the calculator either. It really wouldn't take much to put 3 extra buttons on the calculator and program it in. It wouldn't. So anyway, probably, yeah. So anyway, we're going to do the sine here. Let's plug in what we know. So this will be sine of 18.43 equals, the opposite is x over my hypotenuse of 10. So I'll put this over 1. I cross multiply and divide. We're dividing by 1, so I don't even have to do it. So this is sine of 18.43 times 10. We get 3.1615 inches. Why did they go up to 4 decimal places there? Yeah, because you're now talking gauge blocks, which go down to a 10,000. Or a tenth if you want to use your slang. Well, jargon, your industrial jargon, how's that? So we got 12 degrees, 40 minutes. And I want to know what height I have to create here. Obviously, there's a reason this is called a sine bar, because it goes off of the sine, right? We're always going to have the hypotenuse, because that's the machine length of the sine bar. And we're always going to be looking for the length of the opposite side. Or we're going to know the length of the opposite side and be looking for what angle it creates. But anyway, so 10 over x, once again, so run. The reason I want to do this example is how do we enter sine of 12 degrees, 40 minutes? Well, you can go through, your calculators have the degree, minute, second button, but on my calculator, it's easier for me to just do sine of 12 plus 40 divided by 60, close parentheses. Why did I do that? Well, because there's 60 minutes in a degree. So that's 12 plus 40/60ths of a degree is what I just put in there. It won't round it off because it's a repeating decimal. I won't have to put type the decimal back in. You could just hit the degrees and then type in 60 and hit the minutes button on your calculator too. Oh, you're right. I did that backwards. Thank you. Thank you very much. Yeah, I was just getting too quick there. Yeah, this should be x over 10. Thank you. So I've got that. Then it's times 10 equals 2.1928 inches. What do you think? Yeah, no, that would have been bad. Find x in your notes quick. 3.6488. Everybody agree? You end up with sine of 21 degrees, 24 minutes. Equals x over 10. So I'm just going to type in sine 21 plus 24 divided by 60 times 10. 3.6488. Not so bad. Well, then let's look at another application. By now you should know this as a taper. It's a rounded piece of stock whose diameter changes over a certain length. Remember, we defined a taper as big diameter minus little diameter over length over 12. The change in diameter in inches over the length in feet. So it's inches per foot is what a taper is defined as. Well, what we're going to be looking at here is finding that angle. It's called a taper angle. And what the taper angle is, if you're looking at this two-dimensionally, is you have this distance here, which is half of the difference in your diameters. It's the difference in your radius, but half the difference in the diameters. And this distance here, which is just the length of the piece. You had your L here. So, excuse me. Let's say we have a 1.875 inch diameter here and a 0.75 inch diameter here. Now in this case, the length must also be in inches, not in feet. For the taper, we wanted the length in feet. But for this, we want the length in inches. So let's say this happens over 8 inches. So the triangle we have right here that we're going to be pulling out of this, here's our angle. This is 8 inches. We know that much. This piece here, that's going to be 1/2 of 1.875 minus 0.75, which is what? Not quite 1 1/4. 1.125, right? Divided by 2. So divided by times the 1/2 or divided by 2 is 0.625, right? Is that right? 0.5625. How about I use my calculator? 0.5625. Is that correct? You get confused, Richard. You got her?
Why do you, at that point, I'm saying I got 1.5 instead of 1.65?
So you're putting in 0.5 times, parentheses 1.875 minus 0.75. So you punch something in wrong.
Times it by half.
Yep, times half or 0.5. Now what yours may have done is you may have done subtraction then minus 5, or times the 0.5 at the end.
Yeah.
And what will happen is if you don't put the parentheses in there, it'll take the 0.75 times 0.5, and then it'll subtract it, and that's how you get 1.5 for that. So this is 0.5625 inches. So to find that angle, we have the opposite side and the adjacent side, which are cotangent or tangent. We're going to use tangent. Tangent is opposite over adjacent. In this case, we're looking for the angle, so we know the opposite is 0.5625. The adjacent is 8. When we're looking for an angle, we use inverse trig function. So use the inverse tangent to get rid of the tangent. Use the inverse tangent of that to get that our angle is second tangent 0.5625 divided by 8. 4.02 degrees. What do you think? Good stuff?
Question.
Yeah.
If you have a paper, like a large end and the smaller end, and the smaller end is off center.
Then that's not a true taper.
Okay.
A true taper has an axis. Then it gets a lot more complex too.
I was going to ask about that because last night I was machining parts that were yay big around and they were off center by that much.
Yeah.
You had to chuck on the ID was off center and then
Yeah.
it turned.
Yeah. Yeah, that's a tough. We're not going to get into that. Not right now, at least. So anyway. We've dealt with problems similar to this.
Didn't like it very much.
You did, kind of. So let's hit this angle here is 80 degrees. We're going to put this at 3.25 inches. And this here, 1.250 inches. I want to find this height. Well, the good news is now that we know trig, this is going to be a lot easier problem. Using just the ratios, it's kind of a pain. But we can do this. We know that the radius of that circle is going to be perpendicular, form a right angle at that tangent. And we can cut this in half. From the rules we learned from our circles in the last unit, we know that if we connect the center of the circle to this intersection of the two tangents out here, what does it do to this angle? Cuts it in half. So it's 40 degrees. So what we have here is we have this triangle. This is a right angle. This is 40 degrees. We got to know a side from somewhere. Well, this is a radius of our circle. We want to know this. So what we have here, according to our angle, this is the opposite side, and what we're looking for is the hypotenuse. Opposite and hypotenuse are sine. So we're going to plug in, we know our angle is 40 degrees. Our opposite side is 0.750. We are looking for the hypotenuse. So now we do have to cross multiply and divide. 1 times 0.750 divided by sine of 40. .167 inches. Everybody follow that calculation? So what we just got was from here to here, 1.167. We also know that from here to here is 0.750. How do we know that? It's a radius. Very good. So now we have a total height found by adding those three. 0.750, 1.167, 1.250. That all adds up to 3.167. Yes? No? Yes. Guess what? They don't stick out the top. Because the total height here is 3.250. Yeah, draw it out of scale. So it's actually slightly below the top of the V block. But you guys get the calculations, right? Bad example, we'll have to do more probably on Monday. Pretend that looks like a circle. Pretend those are evenly spaced around my circle. What we're looking at is indexing, or spacing holes, a certain number of holes around a circle. Yes. So in this case, we got 5 holes evenly spaced around a circle. And the circle is going to have a radius of 3 inches. We're going to make it easy on ourselves. I want to know the center to center distance from one hole to the next. To do that, I'm going to draw this triangle in here, and I'm going to find this angle. What's that angle going to be? Well, 360 divided by 5 does give us 72 degrees. Where'd the 5 come from? 5 holes. Technically, it's 5 spacings between holes, but there's 5 holes and 5 spacings. So that's 72 degrees. Now, I can't work with that. What I have to do is this. We learned in the last unit that if I draw a radius, or if I draw a line from the center of the circle that hits this is a chord, that hits that chord at a right angle, it cuts the chord in half. So this is going to be half of the whole thing. It also cuts my angle in half, so this is 36 degrees. I know this is 3 inches, so I can find this side here. So what I have here is a triangle. It looks like this. 36 degrees, this is 3 inches, and I'm looking for that. So I have opposite and hypotenuse according to my angle, which again is sine. So sine of 36 degrees equals the opposite sides what I'm looking for. My hypotenuse is 3. So sine of 36 times 3 divided by 1. 1.7634. Is that my answer? No, what do I have to do? Double it. 3.5267. Notice I didn't write that down and type it back in. I just did times 2 in the calculator because it is different than the rounded version. I would have been off by a 10,000th if I had rounded it first and then multiplied. Keep it in the calculator as much as you possibly can. Any of these trig calculations, if at all possible, avoid writing it down and punching it back in. For some of your calculators, you can do that, yeah. I believe this should be in the packet I gave you guys yesterday, page 358 through 361.